Hi everyone, and welcome back to Power Electronics Lectures. Today I'm going to talk about how to find the average voltage for a three-phase diode rectifier with line impedance, taking into consideration the effective line impedance. Before going to the three-phase diode rectifier, let's recall the effective line impedance for the single-phase half-wave rectifier and the single-phase full-wave rectifier. The output of a single-phase half-wave rectifier with a freewheeling diode looks like this. When the input is a sine wave, so the output will be something like this during this time period. And we said during this time, both diodes are conducting, and then the input voltage and the output voltage will have 0 volt in them. How to find the time, the commutation time here? We said that you can draw the circuit again here when we have commutation. If we say this is the input voltage, VA or V input for example, the current was flowing in the freewheeling diode first, and then in the commutation the current will start flowing in this direction slowly and slowly. Since the current is increasing in this inductor, so the voltage polarity will be something like this. We can say this is LdI by dt. The current that is increasing at this moment in the green line, so this will be increasing until I out, and the current in the freewheeling diode will be decreasing in this way to 0, from I out to 0. So the current that's flowing inside the input inductance, it will be increasing from 0 to I out. So if we try to write this equation here, so we can say that Vn is equal to LdI by dt, and the input voltage is a sine wave, so we can say that this is a V maximum sine 2 pi t over t, and try to solve this equation. You'll find that LdI is equal to V maximum sine 2 pi t over t times dt. If you take the integral for both sides, you'll find that the integral for this current, L is constant, so the integral for this current is the value that's increasing from 0 to I out, so that the limits of the integration here from 0 to I out, so we'll end up with a value of di integrated to be I out times L. And this will be V maximum, the integration from 0 to Tz for the sine wave. Take the integral for this sine wave, it will be minus cosine wave for this value, and it's divided by 2 pi over t capital. And finally, you will get this equation, which is cosine 2 pi Tz over t capital is equal to 1 minus 2 pi Li out over V maximum t. And from this equation, we can easily find the time duration Tz. And this Tz is what we call the commutation time. All these values are known, so we can easily find the time duration during the mode Z, the commutation mode. How to find the average voltage for this output voltage? We can take the integration from here to here over the whole period t. So this will be from Tz to t over 2, and then we take the average for the whole period, because this is 0 and this is 0 must be taken into consideration. So we can say this is integral from Tz to t over 2 for this sine wave form. So the equation that we obtained, as we said, is equals cosine 2 pi Tz over t is equal to 1 minus 2 pi Li naught, which or I output over V maximum times t. And we can say that this is equation number Z, for example. And this equation number Z for the half wave single phase rectifier. Okay, now easily you can find the value, of course, of the time here, the commutation time from here to here. We said this is Tz. So Tz from this equation is equal to cosine inverse for this value, 1 minus 2 pi Li out over V maximum t, and all this multiplied by t over 2 pi. In order to find the average voltage, you can take the integral for this from Tz to t over 2, but you have to take the average for the whole period for t. Why? Because if you don't take the average for this will not be included, and then we'll end up with an average for only for this duration, which is not right. So the average voltage here is equal to V average for the single phase half wave rectifier, the integration from Tz until t over 2, but here we'll divide by the whole period by t for V maximum sine 2 pi t over t dt. And this value is equal to V maximum over 2 pi times 1 plus cosine 2 pi tz over t. We can take this cosine value from here, from this equation, and substitute it here. So at the end you'll get that the average value for this half wave single phase rectifier is equal to V maximum over pi minus Li out over t. And this is the average value for the single phase half wave rectifier. Now let's have a look at the average value for the single phase full wave rectifier. Why I'm covering this? Because here is something important. The duration time here, the commutation time, it depends heavily on how long the current will stay inside the line impedance. For example, for the single phase half wave rectifier, the current will stay from 0 to Tz, for example, and will jump from 0 to I out. But for the full wave single phase rectifier, the input current is increasing from minus I output to plus I output. So here the duration for the single phase full wave rectifier increases. For the single phase full wave rectifier, we can say easily that this portion is taken or eaten during the commutation. Here we said the input current is changing from minus I out to plus I out. So you can see that here the input current is changing from here. And this is minus I out. Let's say that this is 0, for example, and this is Tz. If you look at this rectifier, you'll find that here we have an input source and both diodes here are conducting, and our inductor here, the input line impedance, will be something like this. Here the current is increasing from minus I out to I out. If the current is increasing, means the polarity applied on the inductor is positive, so this will be LdI by dt, and this plus minus V input, which is the sine wave. So we can simply say that LdI by dt is equal to the input voltage, which is V maximum sine 2 pi t over t capital. Now, distribute this, you'll find that this is LdI for the input current is equal to V maximum sine 2 pi t over t capital times dt. If you try to take the integration for both sides, you'll find that the limits for this integration, for this current, from minus I out to I out. So this will be L times 2I out is equal to V maximum integration from 0 to Tz for the sine wave dt. So this is the only difference here. For the input current will stay from minus I out to I out, which is longer period. Try to find the integration for this. The integration for sine is minus cosine, and substitute with these values. You will easily find that 2I out is equal to V maximum t over 2 pi L times minus cosine 2 pi t over t from 0 to Tz. Some simplification for this equation, you will find that this will be equal to 4 pi L times I out over V maximum times t, and this is equal to 1 minus cosine 2 pi Tz over t, cosine 0, 1. Take this equation here, you will find that cosine 2 pi Tz over t is equal to 1 minus 4 pi I out over V maximum times t. And from this equation, we can easily find the commutation time Tz for the full wave single phase rectifier. I'll call this equation Z, full wave single phase rectifier. Okay. Now the average value for this voltage here, it's the value of this portion, the value here, and we can take the average from 0 to t over 2. And the integration from Tz to t over 2. So the average value here is equal to how much? For this single phase full wave rectifier, 1 over t over 2 integration from Tz t over 2 V maximum sine 2 pi t over t times dt. Now this simply is minus cosine 2 pi t over t from Tz to T over 2 multiplied by 2 times TV maximum over T times 2 pi, T with T, 2 with 2. So here we end up with V maximum over pi times 1 plus cosine 2 pi Tz over T. Substitute this equation here for cosine 2 pi Tz over T. You'll get that V maximum over pi times 1 plus cosine 2 pi Tz over T. And as you said, this is taken from the equation Z, which is 1 minus 4 times pi Li out over V maximum times T. And this is for the full wave single phase rectifier. So here you can easily say that the average voltage here is equal to 2 V maximum over pi minus 4 times Li out over T. And this is the final equation for the average voltage for the full wave single phase rectifier. If you compare this one with the single phase half wave rectifier, you'll find that this is the average voltage without line impedance, and here is the value of the portion that is taken during the commutation. You'll find that this portion in case of the full wave single phase rectifier, it's double the value of this one. This is 4 times L and this is 2 times L. So here is a big difference between the full wave and the half wave rectifiers, because the current inside the full wave rectifier commutation during the commutation of the full wave rectifier stays from minus I out to plus I out. So as if the current inside this inductor going this way and then coming back this way, going to the right, back to the left, and so on and so forth. So this of course takes more time during the commutation, but for the single phase half wave rectifier, it's only one way from 0 to I out. Now this gives us a clear idea how the behavior of the current will be inside the three-phase full wave rectifier. If you remember the three-phase full wave rectifier output voltage here without considering the line impedance, so the output is clear without any portion taken. And we said that we can take the average from here to here, which is T over 6, the duration time here T over 6, because here we have 6 portions collaborating to make the output voltage. And the solution was easy, because we said, okay, we can take the axis from here and we can take the average from minus T over 12 to T over 12. Or you can say that this duration here actually starts at T over 6 and ends at T over 3, and take the integration for this sine wave, or take the integration for these limits for the cosine wave, and find the average for this voltage, which is the average for the output voltage of this three-phase full wave rectifier. No problems about this. Now the problem when we have when we take the line impedance effect, you will find that the voltage here is something like this. Here is the eaten portion, or the missing portion. So we need to know what is the duration from here to here, how long this duration takes, and also we need to know how much is the average voltage for this output voltage. Now it looks similar to this one, but in reality it's not easy. Why? Because we don't know exactly when this commutation starts and when this commutation ends. And also this value here is not placed at the 0 line. So let's find how to find the duration first from here to here, and then we'll see how to find the value that is missing within this output voltage. We already found the value of the average voltage here with no line effect, and we said that this is the axis here from 0, and this is minus T over 12 to T over 12, and we said this is cosine wave 2 pi T over T dt V maximum, and here again we said this is the line voltage. So if we say that the V maximum for the phase voltage, so the line voltage is the root square of 3 times V maximum, integration from minus T over 12 to T over 12. and this is the average voltage for the three-phase full-wave rectifier. Simply, we can say that cosine integration is sine, and this is from minus t over 12 to t over 12. So you will get at the end the average voltage here for the three-phase full-wave rectifier. Simple integration, this will be the root square of 3 times V maximum over pi times sine pi over 6 minus sine minus pi over 6. Calculate these values, you will get that the average voltage is equal to 3 times the root square of 3 times V maximum over pi. This is the average voltage here. If we manage to find the average voltage here and deduct the missing portion from this average voltage, we can find the average voltage for the full wave rectifier with line impedance effect. So now we obtain this value, no problems, without line impedance effect, which is from here to here, all this average. Now let's try to find this value here, this portion, and deduct the value here, this small portion, from the whole average voltage to find this value. Assume that the current is flowing in this direction in a three-phase full-wave rectifier, and the commutation will happen from VBC to VAC, like what we have here. Now the voltage here is VBC, which considers in this current here, the current flowing through diode 3, coming back to diode 6, and the output voltage will be how much? VBC, okay, which is the line voltage. Now at this point here, what happens? We expect that if there is no line impedance, so the voltage should be something like this, right? And this voltage should be how much? Should be VAC. Now the current will be overlapped here, or be jumped from VBC to VAC. During the commutation, the current will flow through VA and also will be through VB as well. So both this branch and this branch are connecting. Now during the commutation here, IA will start increasing and IB here will start decreasing. When we say increasing, so the polarity of the voltage across the inductor will be positive, LdIA by dt, or the common current here, and this will be decreasing, so this will be how much? Plus minus LdIB by dt. The current IB will be decreasing, but there is here circulating current, so this will be in this direction, but the current IB will be decreasing, so the polarity of IB will be reversed here. The polarity of the voltage across this inductor will be reversed. So what we can conclude from this diagram, we can say that plus VB minus VA plus LdIA by dt plus LdIB by dt is equal to 0. And I'll call that the commutation current here, the common current here is IZ. So this can be replaced by 2 LdIZ by dt, which is the common current inside this loop. So again, rearranging the voltage, so here we have VA minus VB equals to 2 LdIZ over dt, the commutation current. And VA minus VB is the line voltage by definition. So this is VAB, the line voltage, is equal to 2 LdIZ by dt. And the line voltage is equal to the root square of 3 times V maximum for the phase voltage, times sine 2 pi t over t. Now our target is to find the duration here, Tz, from here to here. So during this time, we said that the line voltage is equal to 2 times Ldi by dt. If we take the axis here, the 0 axis here, so we can easily say that, so this is 0, and this point is Tz, so nothing stops us from moving the axis here and here, no problems. But at this point, this is not sine 2 pi t over t. I will say this is sine 2 pi x over t, for example. And this x is the shifted sign. So here, 2 LdIZ is equal to the root square of 3 V maximum sine 2 pi x over t dx, integration from 0 to tz, and this integration from 0 to I out. Because here the current is changing from 0 to I out. Integration for sine minus cosine, so this will be minus cosine 2 pi x over t from 0 to tz, the commutation time, and this will be the root square of 3 times v maximum times t capital over 2 pi, and this definitely will be how much? 2l times I out. Some arrangement for this equation, so this will be 2l times I out equals to the root square of 3 v maximum t over 2 pi times minus cosine 2 pi tz over t capital plus cosine 0, which is 1. Some arrangements for this, you will get that cosine 2 pi tz over t is equal to 1 minus 4 pi L times I out over the root square of 3 times V maximum times T. We can use this equation to find the commutation time in a three-phase full wave rectifier. So we can say that Tz is equal to T over 2 pi cosine inverse for 1 minus 4 pi Li out over the root square of 3 times V maximum times T. And this is the commutation time. Now let's try to find the portion here, this portion, and deduct it from the whole average voltage or the whole output voltage in order to find the average voltage for the three-phase full wave rectifier with line impedance. Now what happens at the commutation here? If you look at the phase voltage here, you will find that at this point the phase voltage VB is equal to the phase voltage VA. And during the commutation you will find that these two voltages are sharing the same value, which is VA plus VB over 2 during this period, during the commutation only. So the value of VA here is VA plus VB over 2. Now if you look at this voltage here, the line voltage is equal to how much? Equals to this value minus VC. So the voltage here is equal to VA plus VB over 2 minus VC. So this is the output voltage, V out, during the commutation. To find this portion here, we can say that this portion is equal to this voltage, which is the line voltage VAC, minus the output voltage at commutation. So this portion, let's say this is equal to VZ is equal to VAC, the green voltage, minus the output voltage at commutation, which is VA plus VB over 2 minus VC. This times minus, this will be minus this plus VAC, which is the line voltage, is equal to VA minus VC. This will go with this. So VZ at the end will be equal to how much? VA, 2VA minus VA, it will be VA minus VB over 2. And this is the value of the small portion here on the output voltage. So we agree that the output voltage is the line voltage. So now again, VZ is equal to VA minus VB over 2, which is the value of the small portion from the output voltage, the value here. And we said that during commutation we have this line and this line impedances are connected this way. This is VA, and this is current IA increasing and current IB decreasing. And the current IZ, let's say this is moving in this direction, so the voltage here is plus minus L d I z by dt, and this is plus minus L d I z by dt. And we said that VAB, which is VA minus VB, is equal to how much? To L d I z by dt. So we can easily say that VA minus VB over 2 is equal to L d I by dt. Now this one here, we can substitute this one here, so we can say that VZ is equal to L d I by dt. Now this VZ times dt is equal to L diz. Take the integration for this, and this will start from 0 and at I out. So the output voltage here at the end is equal to how much? L times I out. And this is the value of the small portion here. Now this, of course, during one period here, T over 6, we can find the average value for this portion. The average value for this portion, we can divide it by T over 6. So V, Z average, is equal to how much? L I out over T times 6. And this is the average voltage for the small portion that is taken from the output voltage. Now we can say that the output voltage is equal to this voltage minus this portion. We get the average voltage for what? For the three-phase full-wave rectifier. So finally we can say that the average voltage is equal to the average voltage for this without line impedance minus this small portion, right? Minus this one, the average voltage for this small portion. The average voltage for this one, how much? Is the root square of 3 times V maximum over pi, and we just found this value here. The average for this value is how much? 6 Li out over T. And this is the average voltage for three-phase full-wave rectifier with line impedance. See you next time.